Hi y'all, so in our last video we have come to understand the impact of some of the irradiation with a pure metallic crystal structure, and we saw that how that can impact the stress strain curve. So in summary, we observe higher yield strength. So look at impact of radiation on pure metal crystal. We have higher yield strength. Now we have also the higher Young modulus E, and observe that the metal becomes more brittle. So there's embrittlement that happens. However, we know that in something like steel, we have other elements in other alloying elements inside. So there'll be things like chromium, we have things like nickel. We also have some residual copper from recycled steels, and we obviously have carbon as well. Carbon is very important for steel. So in this alloying elements, how would these alloying elements interact with the radiation damage or the radiation in general? So today let's explore impact of irradiation on alloying elements, or materials with alloying elements. Alloying elements. So we've been talking about neutron damage thus far. Alright. And we know that with neutron damage, we create vacancy plus interstitial pairs. Vacancy and interstitial pairs, these are called Frankel pairs. How would these vacancies and interstitials interact with these elements during the irradiation process? For this, you will need to understand diffusion, and if you want to you need to understand some of the mechanisms behind diffusion. For example, you might want to know what diffusion, we want to know Fick's law, and we might also want to know something called Kirkendall effect. So if you have not understood these, please pause the video and take a look at the link below. You'll probably want to explore some of these concepts. Now I assume you know this already. So let's begin by exploring neutron irradiation effects, because that's very prevalent in a nuclear reactor. Okay, so we have discussed some spectrum of neutrons before. We have a fast spectrum, which maybe is a typically 1 MeV neutron. And when it slows down, pardon the announcement outside. So don't worry about that. Okay, so we have a 0.025 electron volt. These are thermal neutrons. Okay, so when a fast neutron, it undergoes slowing down, or it's also called thermalization. When it undergoes thermalization, it becomes a thermal neutron. It loses energy to its surroundings. Okay, so what can a fast neutron do? We know that it makes Frankel pairs, but when it slows down to a thermal spectrum, what usually happens is that these thermal neutrons will get absorbed. So when a neutron goes through a lattice, okay, it knocks and creates lots of Frankel pairs, and the collision cascades that we have explored earlier, and it gradually slows down after many collisions. Well, if you have a slow neutron come in, or rather it can slow down, and you gradually get thermalized after a very long while. Sometimes you will have this thermal neutron, sometimes it goes back into the lattice, depending on what the medium surrounding the metal is, especially if it's water. If a fast neutron goes through the lattice and still exits with a high amount of energy, but once it hits water or carbon, it can bounce back, it gets reflected back into the lattice, and it gets slowed down. So these thermal neutrons, okay, so I'll put fast here, thermal here. So these thermal neutrons can get reflected back into the lattice, and once that happens, neutrons can go through an N-gamma reaction. Basically, it means it gets captured. So for example, what happens is that if you have copper inside and you have neutron, it will form a compound nucleus. Okay, basically it forms copper 64. So it forms copper 64, and this is in a very unstable state. So now this will decay into nickel 64 plus an electron plus antineutrino. So this is just a beta decay. If you're not sure, can go look it up. But basically, when copper absorbs a neutron, the overall effect is that it forms a nickel. Likewise, this is what happens when neutrons are absorbed into copper. So if neutrons are absorbed into, let's say, some of the native nickel there, it will go through a similar beta decay process, and at the end of it, after decay, it will form copper. Alright, so this is basically neutron transmutation. So this is a very common effect in the inside the steels of a reactor pressure vessel. So even if there is a zero copper inside the metal lattice, okay, you can actually form copper because of the neutrons, thermal neutrons being absorbed. And for you can refer to some of the links I'm placing just for your information. So you can see that it goes both ways, depending on what isotopes are present inside the lattice. Okay, so we already discussed that copper can be transmuted by neutrons, and this would cause radiation damage. Because when these betas come out, they can come out at several keV to MeV, and this can also cause another collision cascade, or it can cause ionization, cause the lattice to heat up, etc., etc. And so nickel can be transmuted to copper, nickel 62 to copper 63, and copper 63 can absorb a neutron to become nickel 64. So these are just some of the typical reactions that can happen. However, and this copper can react with the Frankel pair. Okay, these vacancies and interstitials generated by the pKa cascade, and the pKa cascade or the depletion zone, that can actually cause there are some things that can happen. Okay, so in an alloy, we want to discuss how this happens now. So we have discussed transmutation. Now we want to discuss how this copper interacts with the vacancy and interstitials caused by irradiation damage. So let's say you have an iron lattice, and you have a foreign copper atom here. Okay, and you have a vacancy here. I'll just mark that by an X. Alright, so the vacancy exists here. Likely there will be one of the atoms surrounding it wanting to move to this spot. Now this is just a random process. Okay, so let's say this iron atom moves here. Okay, this is the first picture. This is our second picture. So So 3 by 5. Okay, so we have a copper atom, we have a vacancy here. So now we have a vacancy beside a iron atom. So these blank ones are iron, this one is copper. So we have a vacancy and we have iron atom that could hop into this vacancy, or we have copper atom that can hop into this vacancy. However, the rate at which the iron atom diffuses into this vacancy and the rate at which copper diffuses into the vacancy are different. So basically, iron and copper will compete to move towards that vacancy. But usually copper will diffuse faster or move faster into the vacancy. Okay? So what? What's so important? Well, if we have multiple copper atoms, okay, I should name this as 1. So let's say we have an iron lattice again. Okay, and we have this vacancy here. So which atom will move here? Likely the copper will be faster. Okay, so if the copper moves here, the copper atoms will start joining together. Alright, and they will start nucleating to form its own phase inside. So if we repeat this process many times, so let's say this, for example, is a copper atom. It can move towards here, and then it will form, okay, 1, 2, 3, 1, 2, 3, 1, 2, 3, 5. Okay, so the vacancy will be here. So for example, we will have these 3 atoms nucleate together. And when these atoms nucleate together, they will not likely want to escape into this vacancy here, because now they're more tightly bound. Now they are in their own little metallic phase. So overall, if we have some even mixture of copper plus iron, and we have some vacancies scattered around here, I'll just use the X to denote vacancies. What happens is that the copper will tend to diffuse faster towards these vacancies, and they'll form their own copper precipitate. Okay, so these vacancies will be moving elsewhere, the rest of it will be iron, but the copper will move into this precipitate here, where it's more thermodynamically stable, and this region will be copper depleted. Now what happens if we have precipitates in the reactor pressure vessel steels? Now think about how these locations will move when they meet this precipitate. If I have copper precipitate, and this location is moving this direction, this location will see the copper precipitate, and then it will require more energy to move past this copper precipitate. So this actually impedes this location motion. And what happens as a result, since we are impeding this location motion, the whole thing becomes more brittle. In fact, this is a very big problem that can cause reactor embrittlement. So big that it's one of the reasons that you want to reduce copper content in the steels. And not only that, we don't just want to lower the copper content, we want to lower the copper content, and we want to lower the nickel content as well in some of our steels. Okay, lower the nickel content. Why? Because the nickel can interact with the neutron and it'll still give you copper. So whenever this copper precipitates form, that is a problem. Alright, well, nickel may not form its own precipitate, but copper will. So for our reactor pressure vessel, we want to reduce both nickel and copper content for our PV, reactor pressure vessel. Okay, so what usually may happen in a reactor is that, okay, we have carbon steel, so there's a low nickel content, but when it comes to somewhere that you want to prevent corrosion, for example, it's meeting water, okay, so the bulk of the steel will be carbon, but close to the part that's meeting the water, you'll have a stainless steel with chromium, nickel, etc. that will prevent the rusting from happening. So carbon steel is more neutron damage resistant as compared to this. This is less prone to embrittlement, but you still need some stainless steel to protect it, the carbon steel from water and whatever acids may be inside that may eat up the steel. So composite materials are often used to try and solve this kind of problem. Okay, now can this precipitation phenomena happen with other precipitates? Well, of course. Therefore, we'll need to be watchful of the elements that go into our reactor pressure vessel. And one of the elements that can interact this way is chromium. Yes, it forms precipitates as well, but remember, whenever a precipitate forms here, there's a higher concentration of whatever foreign atom is here. Here will be depleted of that atom. And one of the other atoms that can interact this way is chromium. Now, where is chromium usually found? Chromium is usually found in this stainless steel. Okay, stainless steel contains chromium and nickel. Alright, and this chromium can be depleted from certain regions. So, if you have water, and then normally you have a uniform mixture of iron, chromium, and nickel, and this will help to prevent corrosion. But let's say you have a vacancy, high vacancy concentration here caused by a depletion zone or something like that. Okay. Oh, okay, it's not a depletion zone, it's a displacement spike. Say you have a displacement spike here, caused by none other than our neutron damage. Displacement spike. So there's a high concentration of vacancies here. So what happens is that this tends to pull chromium towards here to form a chromium carbon precipitate. And then what happens? The region here, since chromium has moved out of this region into here, for example, this place will be less enriched in chromium. When it's less enriched in chromium, it becomes less corrosion resistant, and this part actually starts to corrode. So if this stainless steel touches water, this will start to rust. Okay, of course this is a simplified kind of a diagram. Actual fact is that there are grains forming our stainless steel. These are metallic grains. So let's just take, for example, that these are some of the grains that are in there. I'm just drawing them randomly. Excuse me. Just drawing them randomly. And what we will find that is that all these precipitates tend to cluster around the green boundaries when radiation hits. And fast neutrons hit this, they'll cause a displacement spike somewhere here, so that the chromium will tend to cluster at the green boundaries. Why do they cluster at the green boundaries? It's because the diffusion happens kind of faster at the green boundaries, because the atoms are less attached to the lattice. So let's say you have this surface, okay? Let's say you have this surface here, this free surface. This atom here is like bonded to 1, 2, maybe 3 atoms. If there's a vacancy here, you have to just break these 3 bonds for this atom to hop to this place. However, let's say you have an atom with a vacancy in the lattice, and then there's a vacancy here. For this, you will need to break 1, 2, 3, 4, 5, 6, 7. You need to break all 7 of these interactions for this atom to move from here to here. So in effect, diffusion happens faster at the green boundaries. So if we have a vacancy cascade here at the green boundaries, what tends to happen is that the chromium at the green boundaries are being drawn into these clusters, and then at the green boundary itself, the chromium content is severely depleted. So let's do a kind of a zoom in. So this is water. Let's say you have vacancies being created here. So you have these chromium carbon precipitates, which are generally not a problem in that cell in itself, except that over here is low chromium. So the water sees this low chromium and this starts to corrode. This process we see here is known as irradiation assisted. Now this helps to create the process that's called irradiation assisted stress corrosion cracking. Alright, so here it's already started to rust. So how does this stress corrosion cracking occur? We've already discussed the corrosion. So where's the cracking come from? So you have this picture here. Here you'll have some oxide layer. Okay, oxide layer. Now this layer is good because it protects the steel. There's an oxide layer that prevents further rust from happening. But the thing is, this is also brittle. This is an oxide film that is brittle. Well, does this oxide film always stay here? Again, not necessarily, because when this reactor pressure vessel is subject to some external stress, creep can occur. And what is creep? Creep is the plastic deformation of a material below its yield stress. And if you're not sure what it is, you can go and look at some videos on that. I can put some of it in the description. So this is a prerequisite knowledge. Prereq. You need to know what creep is. So creep can come in and cause this oxide layer to fracture. So when there's stress applied to this material, creep will occur, and then this oxide layer will fracture. The water again can go in and cause more rust to occur. Now this is why it's called irradiation assisted stress corrosion cracking. What's the irradiation? It comes from the neutrons, and it causes vacancy and interstitial pairs to occur, and then they form these little precipitates here. And when there's corrosion, it's because of the water eating into the low chromium areas, And when the stress that occurs, creep will also occur, causing cracking. So yeah, this is very similar to something called intergranular stress corrosion cracking. So I just use STC to represent stress corrosion cracking. But the main mechanism, if you have heard of this before, the main mechanism causing this to occur is temperature, which causes something similar like this to occur. And that requires around like what, 600 degrees C for the precipitates like this to form, because you need some kind of activation energy. But for irradiation assisted stress corrosion cracking, that energy comes from the neutron, which causes the displacement spike and the pKa cascade that causes all these vacancies to occur, and then the precipitates will start to form, causing a local area of low chromium enrichment. So what have we covered in this video? We've covered how Frankel pairs, and especially vacancies, can interact with alloying elements such as chromium and copper to kind of cause damage. And we've explored some of the mechanism behind these effects. And hope you have enjoyed this video. I'll see you guys next time. Bye bye.